So for our dynamics project, we decided to do it on the drivetrain motion analysis for the UGA Motorsports BMW E46. This project is by Evan, Raul, Jason, and Nandan. This is the overview of our project. First, we'll do the background, then problem statement, design method, inputs and experimental data, our experimental data, both of the calculations, results, conclusion, and then sources.
Let's start off by talking about the background behind this project. In automotive engineering, especially in motorsports, drivetrain optimization plays a critical role in achieving both acceleration and efficiency. In the transmission system, selection of gear ratios directly influences how torque from the engine is transmitted to the wheels and how fast the vehicle moves at any given engine speed. Understanding these dynamics is essential for tuning vehicles for specific racing environments, and our goal with this project was to apply the dynamics principles we've learned in class this semester to a vehicle's drivetrain. And for this project, we chose to analyze our very own UGA Motorsports champ car BMW E46. By analyzing its drivetrain behavior at fixed engine speed, this project aims to simulate real-world performance conditions where quick acceleration and precise gear engagement are crucial. Using real measurements for the gear ratios, rear differential ratio, wheel diameter, and engine power and torque output, while factoring in mechanical efficiency losses, we aim to compute an experimental number for the wheel torque and vehicle speed across all 6 transmission gears. This will allow us to better understand how the E46 behaves under load and how gear selection impacts its performance.
The problem statement is the goal of this project is to determine the torque delivered to the wheels and the final vehicle speed for each gear of the transmission in the UGA Motorsports BMW E46. By analyzing the drivetrain behavior at a fixed engine speed of 5,000 RPM and a mechanical efficiency of 0.85, this project aims to provide insights into how gear ratios affect output performance.
For the design method of our project, we first needed to understand how the drivetrain of the BMW E46 performs. We started by creating a system model that shows us how power flows from the engine to the wheels. Then we focused on calculating 2 things for each transmission gear. First, the vehicle speed in miles per hour, and the torque at the wheels in pound-per-feet. We based all of our calculations on a constant engine speed of 5,000 RPM and a mechanical efficiency of 0.85, which means 85% of the engine's power reaches the wheels due to losses in the drivetrain. The first step we took was to identify the inputs: the transmission gear ratios for each gear, the rear differential ratio, measured the wheel diameter, engine speed, which was 5,000 RPM, and the mechanical efficiency, which was 0.85. Then we used our equations to find outputs. First, calculate the angular speed at the wheels using gear ratios and the engine speed, then use that angular speed to find how fast the car would be going in miles per hour. Then we use the power equation with efficiency to find torque at the wheels. Lastly, we sketch a system diagram to help us visualize our method.
Because some of the inputs we need for this calculation cannot be easily found experimentally with the time and resources we had to get them from a different source. These inputs were the transmission gear ratios, the engine power, and torque output at 5,000 RPM. The transmission gear ratios were determined by the manufacturer specification sheet as seen on this slide, and the engine power and torque values were found from a dynograph that was made when the exact engine in our car was put on a measurement device called an engine dynamometer, and the values at different RPMs were graphed as seen on the left, and the conversions for the RPM are seen right below.
Now for our experimental data that we actually found. First, we measured the wheel diameter and set the reference points for our experiment. These can be seen in the photos under that section. Second, we rotated the wheel and measured the number of corresponding rotations of the drive shaft to verify our rear differential ratio of 3.07. I'll show these videos now.
Rotate it once all the way back to where it started.
Okay.
No, yeah. Okay, that's one.
Yep.
Two.
So before we get into the calculations, we can go over the governing equations that we're going to use. So we're going to be using equation from 15.1, fixed axis rotation, where we're going to determine the tangential velocity at the edge of the wheel, which will be pretty much the vehicle speed under optimal conditions. So that's going to be tangential velocity equals angular velocity of the wheel times the radius. We're also going to be using equations from chapter 13.1d, power and mechanical efficiency, where power is going to be force times velocity. In the case of our rotational motion, that'll be torque times angular velocity. And mechanical efficiency will be power output over power input. All right, to start off our vehicle speed calculations, we first need to obtain what the angular velocity of the wheel will be in each gear, because this is the value that's going to directly be affected by the drivetrain gear ratios, as the diameter of the wheel is going to stay constant, of course. So we want to convert our known engine angular velocity from RPMs that you see in your tachometer to radians per second for these calculations. So that comes out to be 523.599 from 5,000 RPMs. Then we need to account for the first gear ratio that's going to affect this angular velocity, which is going to be the transmission. So the angular velocity of the engine output shaft, or the crankshaft, times the gear ratio of which transmission gear we're going to be calculating, which we're going to call TR sub X, is going to give us the angular velocity of the drive shaft. So for first gear, which I'll calculate on this slide in more depth, it's going to look like angular velocity of the drive shaft equals angular velocity of the engine times the transmission gear ratio for first gear. And if we use 4.35 from the table for that, we get 120.368 radians per second. So that's pretty much how fast the drivetrain or the transmission output shaft is going to be the same speed. That's how fast those are spinning. All right, but there's also the differential gear ratio that's going to affect this angular velocity. That's the last and final one in this drivetrain. So we need to account for that. Luckily, that's just going to, of course, it's going to stay the same for each transmission gear, so you kind of only have to, that stays kind of a constant for all these calculations. So ours was found to be 3.07. So you do the same thing, plug in, angular velocity of the drive shaft times differential gear ratio of 3.07. So you get the angular velocity of the axles are spinning at 39.28 radians per second, but because those are fixed directly to the wheels, we can pretty much say that the angular velocity of the wheels is the same as the angular velocity of the axles, which are 39.208. And we can also note that both of the axles are going to be spinning at the same speed in this situation because it's driving in a straight line on a flat surface, so that open differential won't be spinning the different axles at different speeds. So now using the final equation, so the velocity of the car is going to equal the angular velocity of the wheels times the diameter of the wheel over 2 that we found, and converted to miles per hour, we got 25.61. So that all that means is if you theoretically got in this car, drove it at 5,000 RPM, in first gear, you'd be going up exactly 25.61 miles per hour. So now we just have to do this for the other 5 gears. So we kind of just did them all here, pretty much the same. The really only thing you're changing is the gear ratio. And we got 44.52 for the second gear, 67.1 for the third gear, 90.57 for the fourth gear, 111.4 for the fifth gear, and 131.06 for the sixth gear. So as you can see, sixth gear, highest gear ratio, you're going way faster than first gear at the same engine RPM. So now we can move on to our torque calculations. We're going to be using the modified equation of power of the engine equals angular velocity of the engine output shaft times the torque of the engine. So we know from our experimental dyno graph that at 5,000 RPM, the engine speed is going to be 198.5 horsepower. And just as a demonstration of this equation, we can actually find the engine torque if you use a conversion factor of 5,252. As you can see there, the torque comes out to be about 208.5 foot-pounds at the output shaft of the engine, which actually does line up almost exactly with the dyno graph results that we're using. So now first, before we get on to calculating, we got to account for our mechanical efficiency of 0.85. So pretty much what that means is most cars range from about 10 to 20% of drivetrain loss. So that the horsepower that comes out of the engine output shaft is actually higher than what gets transferred to the wheels because of different things like rotational inertia, friction, drag, and other things throughout the drivetrain components. And this loss can actually be reduced through aftermarket means like reducing rotating mass, improving lubrication, and using stiffer mounts. These things are pretty common to be done in motorsports and high-performance applications. But we're going to see about a 15% drivetrain loss for our car. So that's going to be a mechanical efficiency of 0.85 is just equal to the power at the wheels divided by the power at the engine. And since we know what the power of the engine is, we can assume that we can calculate that the power at the wheels is going to be 168.7, which leaves 84.36 horsepower per wheel. And to find the torque in one of the wheels at a specific gear, we're going to use our power formula with our angular velocity for each wheel that was found before in the vehicle speed calculations. It's going to be our input. And also note that we must use RPM and not radians per second because of the way we set up this equation. So power in the wheel times 5,252 equals angular velocity of the wheel times the torque of the wheel. Since we're finding the torque, if you plug in the angular velocity for the wheel in first gear, as we found before, you get a torque value of 119.899 foot-pounds at each wheel in first gear at 5,000 RPM engine speed. So now solving for the other 5 gears, as you can see here, we did that kind of the same way we had before. And you'll notice that these results are not as linear as the vehicle speed was, and you'll see that in our results graph on the next slide. So as you can see in our results, we graphed transmission gear to vehicle speed first, and you can see it looks pretty linear when graphed. This is likely because the gear ratios were just chosen to be evenly spaced when designing the transmission, but the ratios themselves are not linear. If you were to plot them, like you can see the difference between 1 and 2 is much greater than 5 and 6. And The transmission gear versus wheel torque graph appears to have more of an inverse exponential relationship, as lower gears are disproportionately more torque than the higher gears. And then this kind of makes sense, is that trade-off of low gear ratios being more torque and less speed versus high ratios being the opposite is purely dependent on the specific ratio for each gear. So we can see for first gear, for example, it's a much lower ratio or higher numerical ratio relative to fifth and sixth gear. So it takes far more rotations of the crankshaft to turn the drive shaft just once. And because our power equals force times velocity, and then force or torque in this case, it has to increase to conserve energy. Because if you're increasing that velocity and keeping power the same, your force has to increase. So that's why lower gears have more torque. And also possible sources of inaccuracy for these theoretical calculations are margins of error with that experimental dyno graph that we used. It was also, could it be slightly different from our engine based on what the company that produced that used, and what, how many miles and wear and tear that engine had. Also, inaccurate measurement of the wheel diameter could be a big one. And those countless, real world conditions that we kind of set as constant, that, road surface, is the car going in a straight line? Is the tire slipping? Does it have deformation? Is it a smooth road? Things like that can all, either change our results in a more minor way, or some of those can make huge differences in these results. So it's important to note that these are purely theoretical results.
So to conclude, these findings, and more importantly the physics behind them, can be applied to optimize drivetrain tuning and selections for more competitive performance in motorsports applications, and when engineering drivetrain systems. The different mechanical systems in cars are a great real-world application of so many of the engineering principles that we learn, all in one machine. We recommend that the principles from this experiment can also be applied when learning how to more efficiently drive a car in a high-performance situation. We have shown that being in a higher gear will allow higher vehicle speeds with more engine efficiency. Meanwhile, a lower gear provides more torque and therefore acceleration at the expense of top speed in that gear and a higher engine speed. A skilled driver will know how to most efficiently balance these trade-offs to choose between the best gear and time to shift. A good engineer will know how to choose the best combination of gear ratios for the purpose and use of the car when designing or modifying the drivetrain. Because we had to use already found experimental values for some of our inputs, and we also could not drive the car to actually verify any of our results experimentally, it is important to note that these calculations are merely theoretical, which should be fairly close to a real-world test.